So it turns out that for atoms of the same element, you can have varying numbers of neutrons. The number of neutrons can vary for atoms of the same element. This is kind of surprising, and it is something that Dalton didn't know about. He said that all the atoms of an element have the same mass, but if the number of neutrons can vary from atom to atom, they don't all have the same mass. In other words, not all hydrogen atoms have got the same mass. Not all carbon atoms have got the same mass. Let's look at that a little more closely. You can have a hydrogen atom with a proton in the nucleus. It's atomic number 1, right? And it's got to have how many electrons? It's got to have 1 electron to balance off that proton in the nucleus. So let's write down the nuclide symbol for this. First of all, if I know there's 1 proton, I know the atomic number is 1. My process goes like this. I know it's atomic number 1, so I'm going to look at a periodic table and see which element has got atomic number 1. It's hydrogen. So I know the symbol that I'm going to use in the nuclide symbol is a 1. I also know the atomic number is going to be 1 because that's how many protons I've got. And the mass number is the number of protons and neutrons in the nucleus. Well, that's 1. There's no neutrons. And you can write down the nuclide symbol for this form of hydrogen, but you can also write down a name for it. You can name the element, and then you can follow it by the mass number. So they can call this hydrogen 1. Now, why bother calling it hydrogen 1? Why not just hydrogen? Well, because the number of neutrons can vary. You can have another form of hydrogen that is found in all water on Earth. And it's a little bit heavier. It's a lot heavier, actually. It's double the mass of a normal hydrogen atom. Heavy hydrogen. Or they used to call it deuterium. Now, I'll write down that name because you might see it again. People still use it. Deuterium, they call this special form of hydrogen. Let's write a nuclide symbol for it. It's got atomic number 1, so it's still going to be hydrogen. It's got mass number 2. So atomic number goes down here. The mass number goes up on top. Remember, they're top heavy. The mass number always goes up on top. That'll keep you from mixing these two numbers around. And then you'd call it hydrogen 2, because you have to use the mass number here in the name. So that's hydrogen 2. Now when you have multiple forms of the same element, and the thing that's different about them is how many neutrons you've got in the nucleus, you call those isotopes. These are 2 isotopes of hydrogen, you can say. There is a third isotope, which is pretty unstable, which looks like this. Now when I say unstable, there's got to be something to hold the nucleus together. And if you've got a couple protons in there, protons will try and kick each other apart because they're both positively charged, and the nucleus would fly apart. That's not the case here. But you've got to have the neutrons act in a way that kind of glues the nucleus together. And if you have the wrong number of neutrons in a nucleus, the nucleus can be unstable. So there's a certain magic number of neutrons you can have with a certain number of protons to have a non-radioactive element. This one they used to call tritium. If we wanted to write a nuclide symbol for it, it's still hydrogen because it has atomic number 1. It has mass number 3 because there were a proton and 2 neutrons. And we name it hydrogen 3 because that's the mass number 3. Okay, so those are 3 different isotopes of hydrogen. Other elements have got isotopes too, and they stopped naming all the isotopes like this when they started to realize how many there were. Let's look at chlorine. Chlorine has 2 isotopes. Chlorine 35 and chlorine 37. Let's count how many particles you have in each of these. Okay, just from the name. Now it's chlorine, and they're giving me the mass number here, but if I'm going to count particles, so I want to do something like this. I want to make a table. Number of protons, number of neutrons, and I could put number of electrons in there too, I guess. Let's do it like this since I'm running out of space here. Okay, I got to have the atomic number in order to count how many protons I've got. Got to have a periodic table. I'm going to look for chlorine. There it is. It's got an atomic number 17 on top. So there's 17 protons, and it's going to be the same for this one too. Chlorine is chlorine. Doesn't matter what the mass number is. It always has to have 17 protons. That's its atomic number. Now how about neutrons? Neutrons is going to be the difference between 35 and 17. So what's that going to be? 18, right? And what's the number of neutrons in chlorine 37? Well, it's got 2 more than that, so it's got 20. You can double check my math. If you add up the protons and the neutrons, you should be getting the mass number that's after that. How about electrons? Well, the number of electrons are going to be the same as the number of protons unless they tell me there's a charge, and there isn't. They're not telling me anything about any charge. So I can just copy the atomic number down there, like that. So you should know what isotopes are. They are atoms of the same element that have got different numbers of neutrons. And there you can say that a couple different ways. You can say isotopes are atoms that have the same atomic number but different mass numbers. You can say it like that as well. You can say isotopes are elements or atoms that have the same atomic number or the same number of protons but different numbers of neutrons. Same thing. Saying it both of those different ways is saying the same thing.